So we're talking about the energy audit that we did here in terms of plug loads. So we're going to go through, by the way, is everyone still awake? Not if you are. No? Okay. Excellent. We're going to go through the overview of aggregate plug loads and auditing methodology, not necessarily in that order. An overview of kind of plug speciation. And by that, I mean, what is on every floor of this building? So just some introduction here. 10 minutes, right? Yeah, okay, good. So plug loads consume 1/3 of building energy sometimes. And since 73% of total energy is produced is consumed in buildings, roughly 30% consumed by plug loads, according to this. This is a concern. They're categorically fragmented, they're spread throughout the building, and they move and they change, and we don't really know what's in there, we don't know if it's going to stay, we don't know whose it is. Well, we do, they don't. They being everyone else. And so what we want to do is we want to make it easy to collect plug load information, designed for incremental deployment. That means that I don't have to do it all in one day, but I could if I wanted to. And we want to derive value from infrastructure. That means that I don't want to put in a sensor that is useless. I want to put in a sensor that is more useful than that sensor should be. And I can do this through intelligent software. And then where I can, I want to encourage building occupants to participate. Introduce Energy Lens, which is the development of one of my colleagues, George Ortiz, who could not be here today. He's on the East Coast in New York. And he was critical in developing and maintaining this audit. And so we have Acne Sensors. You may have noticed, if you were upstairs with us, a bunch of little sensors plugged into the walls. They monitor the energy use of plug load devices and are capable of reporting that energy use in about 10-second increments. We have smartphones, much like mine, that we can place barcode scanners on. And so we combine these two things to have live streaming data that we can scan a tag on a barcode and on a sensor and get data. And so the formatting doesn't like me either. So this is a QR code that you could scan and get some sort of data out of. And so we can move them around, and we can encourage the occupants to participate by having their phones out and assessing the data available to them. And so tag everything. There should be a comic to go along with this. But essentially, everything in the building that I could get my hands on has a QR code on it, and it is tagged, and it is in the database. If it's part of the load tree, that allows us to kind of dive down deep and say, okay, what is this segment of the load tree telling us, and how can I derive information? Are there a bunch of printers on this floor? Are there a bunch of computers on this floor? What is the schedule of this floor relative to devices on it? As we'll see in just a minute, then that varies. And so we're going to classify, locate, and derive the relationship between things. What room are they in? And that helps us process streaming data. And so real quick, with beautiful art, we're going to demonstrate the process of adding a device that I did upstairs. First, you register the QR code. This is you, by the way. And you swipe the QR code and enter some information. And then you add it to some sort of sensing system. Is this attached to an Acme reader? Is this attached to a computer? Is it a part of a power strip? And then you can get data on it just by swiping it. If it's attached to a meter and you scan the device, it will pull up a graph of its power use. I just want to point out, nobody else can do that right now that I'm aware of. And so you can check out the Energy Lens website that my colleague has set up and see all of this data and some examples where you don't need to have a smartphone. But I want to real quickly I think I just used up half my time, talk about plug loads in Citris die hall. This is an aggregate. This is one day's plug loads in the form of a series of 7 meters stacked on top of each other and put into one graph. So as you can see, the spikiness, this is all your laser printers and your tea kettles and your coffee makers, and it's relatively stochastic. We can't really control that. But what we do know is that, first thing, there's about 33 kilowatts being used in the middle of the night when nobody's here. David Culler would say that we are doing nothing and we're doing it poorly. We need to be doing nothing well, and we're not. And then we build up this peak, and later I'll show you a load duration curve that illustrates this peak. But I want to turn this graph on its side and stack it up and see how it compares to days. So this is October 12th, just as a representative day. This is the whole month of October. And if you can see, that graph we were just looking at, it's right here. But I've turned it on its side, and now it's color-coded instead of coded by its height. And so what we can see out of the building are these patterns. We can see that typically the users come in the morning, around 9. There's some variation of when the peak gets going, but there's a relatively consistent peak going through the day. And sometimes we don't have sensor data because things fail, which is a research opportunity. What am I doing for time? Good, excellent. All right, cool. Somebody's doing something on Thursday night. I don't know. I think they're playing video games or running simulations, whatever scientists do on Thursday nights. And we can see that the building uses a lot of power, and it uses a relatively consistent peak. But let's break it down. Let's look at the second floor. And I know from auditing the second floor that this group here is users coming in and plugging in laptops. They're turning on LCD screens. But all these little spikes in the middle of the night are from the cafe. And I suspect that this large jump is from a computer lab on the floor. And we can determine this kind of behavior as a future research question by having roaming fleets of sensors that collect streaming data in conjunction with this audit. We never made it to doing that on the second floor, but we have been doing it on the fourth floor. And so, formatting error. This is the third floor. This is where we're sitting. I would suspect that right now it looks kind of like that. This is a different ecosystem. This has a few users that live in offices. And once again, there's something going on overnight at some points during the week. This might be a large printer. But on Wednesdays and Fridays, there's seminars at noon. If you look there. We can pull this information out and determine when the peaks are during the week, and we can shift other loads in the building depending on that. This is floor 4. Floor 4 is occupied by students like myself. And I don't get out of bed as early as the workers on the 5th floor. So I get in here a little bit later, and I stay a little bit later. And that's pertinent to planning our energy usage. There are some printers. There's a lot of base load here that I have pretty much concluded is derived from computers being left on. And then there are, on the 5th floor, a more regular schedule. This is what happens when you have office workers. These are all people who come in. Most of them are professionals who work in the nano lab. I think the nano lab workers like their days a little more structured than I like mine. So they're in here and working 9 to 5. It's pretty regular. We can do analysis on this to kind of derive the shape of that and plan around it. And then this is floor 6, another student floor. We can see the irregularity here. And then this one I think is the most interesting to me. Anyone want to guess who lives on the 7th floor? I'm going to call on one of you if nobody guesses. Air condition? Computer scientists. As you can see, the 7th floor has very little load variation. It hovers between 7 and about 10 kilowatts most of the time. And these are people running simulations a lot, I guess, or they're charging their robot. There's a big robot up there. But the point is that this is an example of a floor where loads are not very shiftable. The computers, which are what consume a lot of the constant load, need to be on. The computer scientists can't work without them. Now, I don't know if they have power saving mode, but this is a place where it'd be very inconvenient to shift load. And later today, I'll go through load shifting based on inconvenience. And so I want to end by showing a last piece of motivation for this work. This is the load duration curve of every day in the month of October last year. Does everyone know what a load duration curve is? Good. So a load duration curve is a curve that indicates how often a certain amount of load is used. It's basically a time series of the power draw sorted by time. And so this indicates that only for about 2 hours a day, on average, for most days, we're drawing more than 70 kilowatts. If we can knock that off by shifting loads, then we will be having a 20 kilowatt cap on our power use throughout the day in terms of demand response respective to plugs. I think that's it. Anyone have any questions? Go.
I have a question. Is the system capable of determining that the light bulb is burned and send a maintenance crew?
We're not that cool yet. Anyone else?